Questions 21 through 25 on the 2009 Grade 9 Pascal Math Contest. Alice rolls a standard 6-sided die. Bob rolls a second standard 6-sided die. Alice wins if the values shown differ by 1. What is the probability that Alice wins? Because we're only dealing with two dice, it won't take that long to write out all the different possibilities, so I'll do that. And these are the possible variations. So our probability obviously is going to be something over 36, because there's 36 different possible ways the dice can end up when you roll them. Now our specific condition is that the values have to differ by 1, only 1. Okay, let's circle those. Here's one scenario. The values differ by 1. This one, this one, this one, and 3, 4. 4, 3, and 4, 5. 5, 4, and 5, 6. And finally 6, 5. So how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 over 36. In lowest terms, that is 5 over 18. So number 21, the answer is C. In the diagram, PQ and RS are diameters of a circle with radius 4. If PQ and RS are perpendicular, what is the area of the shaded region? I'm going to call this region here A. And this region, of course, will also be A. So the area of the shaded region will be equal to the area of the full circle, which is pi r squared, minus 2A. So if we can figure out A, this will be no problem. So let's first concentrate on figuring out A. And how do we do that? Well, the first thing I'm going to do is sort of connect PR and SQ. And I did that to sort of show that, not that it really was necessary, but that this is kind of like a square, right? I think it is a square. And the key thing here is that there's one line in this question that really helps. It's this one right here. PQ and RS are perpendicular. That's very helpful. Why? Because if PQ and RS are perpendicular, then that means this is 90 degrees right here. And therefore, that means that this triangle is going to be very easy to figure out in terms of its area. So A will be the circle pi r squared divided by 4, because this segment of the circle is basically a quarter circle, because that's 90 degrees, minus the area of that triangle, which will be, of course, 1/2 base times height. But the good news is that the base is just the radius of the circle, which is 4, and the height is also 4. So 1/2 4 times 4. So pi r squared, well, r is 4, so that's 16 over 4, and this looks like 16 over 2. So this becomes 4 pi minus 8. And there we go, we just got A, so we can now calculate area of the shaded region. Pi r squared, well, r is 4, so we have 4 squared minus 2 times A, so 4 pi minus 8. So this becomes 16 pi minus 8 pi plus 16, and therefore this is 8 pi plus 16. 8 pi plus 16 is choice E for number 22. A $1 coin should have a mass of 7 grams. Each individual coin may be lighter or heavier by as much as 2.14%. Joshua has a number of these coins and determines that they have a total mass of 1 kg. What is the difference between the greatest possible number and the least possible number of these coins that he could have? The word exactly is missing here, and I'm pretty sure they should have put that, a total mass of exactly 1 kg. And I'll talk a little bit about that soon. But first, let's just figure out what is 2.14% of 7. It is 0.1498. So the range in terms of the weight of this coin is the heaviest will be when it is 7 plus this, which is 7.1498. And the lightest that the coin could be is 7 minus that. So that would be 6.8502. Okay, so we look at both. First, let's look at the, doesn't really matter, lightest one. So that means 1 kg is 1,000 grams divided by 6.8502. And if you do that, you get 145.98. Now, obviously, you can't have 145.98 coins. It has to be a whole number. So what do I do here? Do I go up or do I go down? Well, let's look at what this would mean. If I have 145 of these coins and they're all 6.8502, they're all the lightest they could possibly be, it results in 993.279. And that's not equal to exactly 1 kg. But what I can do is I can make each of these coins a little bit heavier, right? Because remember, lightest means that absolute lightest, but any of the coins can be a little bit heavier. They can be exactly 7, or they can be up to 7.1498. So what I can do is to make it exactly 1,000, I can take 145 coins and I can divide 1,000 by 145. And if I do, I get 6.8965. And this is perfectly allowable because I can make each coin a little bit heavier than the lightest. So I'll just put that in, can make coins heavier. Okay, so 145 coins, and if they are on average that much in weight, 6.8965, it becomes exactly 1,000. So this is good. So that means I can have 145. So that means that 145 represents the greatest possible number of coins, because the lighter the coins are, the more coins you will be able to have. So that takes care of half the question. Now let's turn our attention to the next part using this guy. If we have 1,000 grams and I'm using the heaviest possible coins, this gives me 139.8, approximately 86, I think. So that means that obviously I can't have 139.86, so I have to decide. What do I do here? Well, let's figure this out. If I have 140 coins and I multiply them all by the heaviest possible weight for each coin, I get 100 or 1,000 times 972. Now, it's got to be exactly 1 kg, so this is a little bit too heavy. But what I can do is I can make each of these 140 coins a little bit lighter to make it exactly 1,000. So I'm going to take 1,000 divided by 140, and if I do, I get 7.1428. And that's perfectly fine because I can make the coins lighter. Can make coins lighter. So this is perfectly fine. I can take 140 and make them a little bit lighter, but I cannot take 139 coins and make them heavier, right? Because this is the heaviest it can possibly be. So I hope that makes sense. It's a little tricky of a question, I think, but it's a good question nonetheless. And this 140 represents the least possible number of coins. So they want the difference, right? So they basically want you to take 145 and 140 and get the difference. And the difference, of course, is 5. So number 23, the answer is B. 8 identical spheres, each of diameter 20, fit tightly into a cube of side length 40, so that each sphere just touches 3 of the faces of the cube. The radius of the largest sphere that will fit in the central space, just touching all 8 spheres, is closest to. So let's show a diagram to talk about what's going on here. Here's a diagram of this scenario where you have 8 spheres. As you can see, 1, 2, 3, 4. You can see this guy is 5, 6, 7, 8. And then they have one additional sphere in the middle right there. Now, we have to figure out the radius of that middle sphere. So we have to figure out the radius of that guy right there. So how do we do this? Well, the important thing to understand in this question is that there's a diagonal that if you draw, it will go through the middle sphere and will also go through 2 of the other spheres. And that diagonal is all the way across like that. If I do that, I know it's a little bit difficult to visualize this, but that diagonal from this corner all the way to that corner will go through this sphere. It will go through the middle sphere, which is right there, as you can see, and will go through this sphere. Okay? So the first thing I'm going to do in this question is figure out the length of that diagonal. And the length of that diagonal we can find, but we have to look at a few other triangles first. The first triangle we have to look at is this one right here. That one. That one has dimensions as follows. This is 40 and this is 40, right? Because the side length of the cube is 40. So I can easily figure out this length. I'll just call it D1. Doesn't really matter what you call it, but so D1 squared is 40 squared plus 40 squared. And therefore D1 squared is equal to 3200, and if you take the square root, D1 is equal to approximately 56.568. Now I can take D1 and, considering that's a right angle, and this side 40 to figure out D2, which is the big diagonal that I'm most interested in. And therefore D2 squared is going to be D1 squared plus 40 squared. And D1 squared was 3200, and then 40 squared is 1600. So D2 squared is 4800, and therefore D2 is equal to 69.28, like that. So that's the first part of the question. Very important to figure out D2. Now I have to figure out what is the radius of that little guy or middle guy, the middle sphere. So how do I do that? Now, it's going to be a little bit messy for me to draw on here. So what I'm going to do is just draw the diagonal down here. Just a line like that. Okay? Now this diagram, remember, I want you to understand that this is 3D, right? This diagram, obviously. But this diagram, I wrote it in a way that obviously it looks 2D. But I want you to just be convinced that this sphere is this one right here. Okay? This middle sphere, obviously, is the middle sphere. I think that is easy to understand. But then this sphere is here, but it's over here on the 3D diagram. It's over on the other corner. Now, this line that I just drew represents my D2. Okay? So that is very important to understand. And the reason I drew it like this is, well, first and foremost, because it'd be kind of hard to draw it in 3D. But I want you to figure out that this is how we're going to interpret this question. Now, a lot of this is something that we already know, but some of it we will have to do a little bit more calculation. Now, what we know so far is that from here to here, that's just going to be the diameter of the sphere. And the diameter of the sphere, we know, is 20, right? They tell you that in the question. So this is 20 right here. And this sphere is also 20, like that. And then the small sphere in the middle, that is the sphere whose radius I'm interested in. So this is going to be 2r right there. That's 2r. Now, the tricky part is, what about this distance right here and that distance? What is that? How do we figure that out? Well, the good news is how you figure out that distance right there, is the exact same concept as how you figured out d2. And that is definitely very helpful. So I'll draw that again as follows. So to figure out this little distance right here, I've got to show you the following. Now picture in this box just one sphere sitting in there. Okay, I'm not going to make the diagram too messy, but just picture that. That box has to have this one sphere, and that will allow me to figure out this little distance right here. So in the very same way, we are going to draw a diagonal from there to there. Okay, and that triangle will also be necessary to figure out that diagonal. And let's start doing the calculations. Now, before we had 40 here, 40 here, 40 there, right? But what do I put in this little box here? Well, to figure that out, we have to understand, what does this point represent? That point. That point represents the center of the sphere. And that is very important, because if we know that is the center of the sphere, then we know that this distance will represent the radius of the sphere. And the radius of the sphere is 10. Okay? So that means this is 10, and then this is 10. So that, in my opinion, that's sort of the hard part of the question. So very quickly, we can figure out this guy. I'll just call that small d1. And small d1 squared will be 10 squared plus 10 squared, which is 200. So d1 will be root 200, like that. And therefore, d1 is approximately 14.14. And then we can use that to figure out this distance, which I will call d2, small d2. Small d2 squared is going to be d1 squared plus 10 squared, and therefore d1 squared is 200 plus 100, and that's 300, so therefore d2 is root 300. And that is equal to approximately 17.32. All right, so that means that we can figure out this distance right here. Remember, this was the center of the sphere. Where's the center of the sphere? It's right here. Correct? So that means this distance I just figured out was d2. So I'll just label that from there to there. And very similarly, on the other side, that will also be equivalent to d2. So that means that is d2. What about this distance right here? That's also d2. This is 2r. And then, of course, what we have remaining from here to here is just the radius, which is 10. And this is also the radius of the sphere, which is 10. So there we go. We have it all. We have the following. This whole distance is d2 plus 10 plus 2r plus 10 plus d2. And that is equal to this whole distance, which we calculated earlier as 69.28. And there we go. we have enough now to solve the question. D2 is 17.32, so put that in here. Plus 10 plus 2R plus 10 plus 17.32 is 69.28. And then at this point we just solve. So I get 2R, put everything on one side, and if you do, you get 69.28 minus 54.64, and therefore 2R is equal to 14.64, and therefore R will be equal to 7.32. That is the radius of the middle sphere. 7.32, and therefore that would be choice B for number 24. Starting with the input Mn, machine A gives the output Nm. Starting with the input Mn, machine B gives the output M plus 3N, N. Starting with the input Mn, machine C gives the output M minus 2N, N. Natalie starts with the pair 0, 1 and inputs it into one of the machines. She takes the output and inputs it into any of the other machines. She continues to take the output that she receives and inputs it into any one of the machines. For example, starting with 0, 1, she could use machines B, B, A, C, B in that order to obtain the output 7, 6. Which of the following pairs is impossible for her to obtain after repeating this process any number of times? We have to look at how this behaves, and I'll just start off with a simple example. You can use any number. I'll use 3, 6. Let's say that is my initial Mn. Okay, at the very beginning. Now, if I put this in machine A, it will give me the output Nm, which in this case is just 6, 3. Now, what is important to look at in this question is factors. When you did this with A, the factors remain the same. In here, both 3 and 6 have a factor of 3, and here you just reversed it, so the factors remain the same. So both 6 and 3 have a common factor of 3 also. Now let's look at what happens when you put the same Mn into machine B. Well, machine B turns it into M plus 3N and N. So M plus 3N is going to be 3 plus 3 times 6, and then the N just stays the same, so we have 6. So this is equivalent to 21 and 6. And as you can see, again, both 21 and 6 have a common factor of 3. And very similarly, we'll do the same thing with machine C. Machine C has the output M minus 2NN, and that would mean this will be 3 minus 2 times 6, which is 12, and 6, and that is, of course, equivalent to minus 9, 6. And again, both negative 9 and 6 have a common factor of 3. So, what does that show us? What does it mean? It basically means that the common factors stay the same after each output. So whether the output is Nm, whether the output is M plus 3NN, or the output is M minus 2NN, the common factor will stay the same. And if you try any number, I just chose 3, 6, you can try any combination. You can try 2, 5, 6, 2, whatever. It's going to show the same. And most of the time, the common factor will be 1. Most of the time. Now, I don't know the exact percentage, but a lot of times, I think, for example, if you started with 3 and 5, 3 and 5 do not have any common factor except 1. So that's what I really mean. That sometimes, I should say, probably better choice of words, some of the time, the common factor will be 1. So that's the first part of the question I wanted to illustrate. Now, what we're going to do is really just look at the answer choices and work with those, because we have to eliminate one. One of these is impossible to obtain with a starting point of 0, 1. So let's look at the answer choices. Let's write them out. And each of these, what we need to do is look at what are its prime factors and then see which ones have a common factor. So 2009 is 7 times 7 times 41. And I'll do the prime factors for each of these. And when you break them all into prime factors, you will notice that only 2 of these actually have a common factor other than 1, right? Any 2 numbers are going to have a common factor of 1. But there's only 2 numbers that have a common factor other than 1, and that's 2009 and 1008. They both have a common factor of 7. And what I'm doing really is I'm comparing 2009 to any of these 5, right? Because if you look at our answer choices, 2009 has to be paired with one of those other 5. So that's what I really meant to say. The only of these 5 that has a common factor with 2009 is 1008. Only 1008 has a common factor other than 1 with 2009, and that common factor is 7. So that means that anytime you're going to go and make 2009, 1008 as an output, that means what you input, mn, these 2 numbers must also have a common factor of 7. But remember, we start with what? What is our initial pair that we're starting with? We start with the pair 0, 1. And if we're going to start with 0, 1, 0, 1, neither of these numbers has a common factor of 7. So since 0 and 1 do not have a common factor of 7, it is impossible to go from 0, 1 to 2009, 1008. All the others are possible because their only common factor, for example, if you paired 2009 and 1016, those 2 numbers, the only common factor is 1. And can you go from 0, 1 to this? Sure, because these 2 numbers also have a common factor of 1, right? 1 is a factor of 1, obviously, and 1 is a factor of 0. I mean, 1 is a factor, 0 has anything as a factor. So that's basically how you figure this out. It's a little bit difficult, it's a little bit abstract, but I hope this makes sense. So the only one we were not allowed or not possible to get for this question number 25 was 2009 and 1008, which is D.